All right, we're going to do some probability in chapter 3. So, probability is an interesting subject. It gets very crazy. We're not going to go there, but they have whole semesters on probability. So if we had a die and we threw a die, so a six-sided die has each of the numbers from 1 to 6 on each side. So, of course, the largest number you can get is a 6. Well, if you roll two of them and they ask you the probability of rolling a 14, well, that's not going to work because the largest number on either die is 6. Well, 6 plus 6 is 12. So it's impossible to roll a 14 if you're rolling two six-sided dice. Now, with heads and tails, as long as you have a fair coin, the probability of choosing or of getting ahead would be 50-50. We call that an even chance, right? 50-50 chance of getting heads, 50-50 chance of getting tails. Then the probability that the sun will rise, well, it's definitely going to rise. We might not be able to see it, but it's going to rise. And so that probability would be certain. A little bit of vocabulary here. A probability experiment is an action or a trial. So like throwing the two die or throwing a coin, tossing a coin, excuse me, getting heads or tails. Now the outcome is going to be the different outcomes that you can get. So if I am tossing a coin, I'm either going to get heads or I'm going to get tails, right? Those are my two outcomes and so those are my possible outcomes that would be in a sample size. Whereas if I'm rolling, let's say, a single six-sided die, I could get a 1, a 2, a 3, a 4, a 5, or a 6. And so that would be my sample size. We're going to look at those in just a minute. Okay. So let's take a look here. We're going to look at a survey where we ask people for their blood type. So that would be O, A, B, or AB. And then we're going to ask them to let us know if they're Rh positive or Rh negative. And we want to determine the number of outcomes and identify the sample space. So what we're going to do first is lay out a what we call a tree diagram. And so first they're going to tell us what blood type they are. So O, A, B, or AB. Then second, they're going to tell us if they're Rh positive or Rh negative. So we have O positive, O negative, we have A positive, A negative, and so on. So that tells us that we've got 4 blood types, but then each of those blood types is divided into 2 Rh levels. So therefore, we're going to have 8 outcomes, and our sample space, is actually all of these 8 different outcomes that we could get. All right, so let's try another one. For this one, we're going to toss a coin, and then we're going to throw one die, a 6-sided die. So when we toss the coin, we are either going to get heads or we're going to get tails, right? So let's say we get heads. Well, now that we've tossed the coin and we got heads, now we're going to toss the die, and we have 6 different choices. Because it's a 6-sided die, we could get any one of those 6 sides, and so we could get heads and then a 1, heads and a 2, heads and a 3, and so on. And then the same thing could happen for tails. If we get a tail first and then we throw the die, we would also have those 6 choices. So we actually have 12 different outcomes. Our sample space would be the H1 through H6, the T1 through T6. So now they want to just look at what we call events. A simple event is if there's only one outcome. So if they ask me, okay, how many outcomes would I have if I want you to toss a head and then roll a 3? Well, there's only one way to do that. We toss a head and roll a 3, right? But let's say they say, okay, but let's toss a head, but then roll an even number. Well, that's not a simple event because we have 3 different ways that could happen. We could toss a head and then roll a 2, toss a head, roll a 4, toss a head and roll a 6. So my sample space is H2, H4, and H6. That is not a simple event because I actually have 3 outcomes. All right, let's look at another example. So for this probability experiment, we had a survey, and we first asked, does your favorite team's win or loss affect your mood? And we let them answer yes, no, or not sure. Okay, so does your favorite team's win or loss affect your mood? And that's these first set of bubbles. So yes, no, or not sure. Then they asked if they were a male or a female. So we have 6 outcomes because if they answer yes, they could be yes male or yes female. No would be no male, no female. And then not sure would be not sure male or not sure female. Okay, so let's look and see. Let's look at the events and see if they're simple events. So one, they say, checking yes for a male respondent. Well, there's only one way, right? There's only one bubble here that is yes and male. So that would be simple. Number 2 is checking no. So checking no, there's 2 choices. We could check no and be a male, or we could check no and be a female. So there's actually 2 choices for that. This is supposed to be a 3. I got a typo there. Then we have not checking yes for a female respondent. So we know they're female. That means we only have 3 choices, but they did not check yes. So we don't take yes female, but we do take no for female, and we take not sure female. And so this also is not simple because there's 2 outcomes. Okay, let's keep looking at sample spaces here. So we ask for a student's age at his or her last birthday. Determine the number of outcomes in each event, and then decide whether each event is simple or not. So we don't want to hear 20 and a half or 18 and 3/4. We want their age at their last birthday. So event C is that the student's age is between 18 and 23 inclusive. So remember, inclusive means we're going to include the 18 and the 23. Well, there's only so many choices because we just want their age. We want an integer. We don't want any fractions or decimals. So we're going to start with 18, and the student could be 18, 19, 20, 21, 22, or 23. So we're including 18 and 23. If that word inclusive had not been here, then we would not have included 18 and 23. We would only want the years between those 2, but it is there. So we have 6 outcomes. That means it's not simple, because to be simple, it has to only have 1 outcome. All right, event D is that the student's age is 20. Well, it looks kind of crazy, but that's my only choice, right? So down here, D is the set of just 20, and since there's only 1 outcome, then it is a simple event. All right, so this one, I have to be careful because it doesn't say the word inclusive. It says randomly choosing a multiple of 5 between 21 and 49. Oh, we did this problem wrong. It's a multiple of 5. Wow, I did every single number. Okay, so it doesn't say inclusive, so I'm not going to include 21 and 49, but this is not correct. We want only multiples of 5. So I already listed all the numbers between 21 and 49, not including 21 and 49. Let's go ahead and grab the multiples of 5 here. Looks like there's 1, 2, 3, 4, 5, right? So there are 5 outcomes in the sample space, excuse me. Right, now we're going to look at the fundamental counting principle. It'll make more sense when I show you an example, but it says if one event can occur in m ways and a second event can occur in n ways, then the number of ways the 2 events can occur is m times n. That's in sequence. So let me show you an example. We are purchasing a new car. we're going to look at 3 different manufacturers, 2 car sizes, and 4 colors. Now we could create a tree like we did in the beginning of the lesson, or we can just go ahead and multiply these, right? Because we have 3 different manufacturers we're going to look at times 2 different sizes of cars. So right there we have 6 different cars we're looking at. And then we're going to look at 4 different colors within each car size, within each manufacturer. So if I straight multiply the 3 manufacturers times the 2 car sizes times the 4 colors, that gives me 24 different options that I can look at. So this is what happens when Sonic tries to tell you that they have thousands of different drinks. Well, they kind of do, because they have a bunch of different sizes, and then you multiply that times whether you get ice or no ice. Then you multiply whether you get a syrup or not. So there's lots of different kinds of syrups. Then you multiply whether you want candy in there, like Pop Rocks. Then you multiply all the fruit they have, and before you know it, you're up into the thousands of different drinks. So that's why Sonic is right, that they do have that many drinks. So this is just a chart from the last problem with the car manufacturers, the 2 sizes, and the 4 colors. And you can see, if you draw a tree, you would also see that there are 24 different cars that you can look at. All right, let's look at access codes. So we have a car security system, and you're going to put 4 digits in. And each digit can be any number from 0 to 9. So if they're any number from 0 to 9, I have 10 choices, right? Because I could type a 0, I could type a 1, I could type a 2, all the way up through 9. So I have 10 choices when I go to put that first digit in. All right, so the very first digit, I have 10 choices, but they're telling me they're not going to do any repeating. Okay, so once you use any number, you can't use it again, right? So I had 10 choices for the first digit that I typed in, but on the second digit, I only have 9 choices because I cannot include the number that I put in the first box. Then for the next one, I only have 8 choices because I can't include the 2 numbers that I put in the first and second digit, and so on. So for this one, there's only the 4 digits. So I have 10 times 9 times 8 times 7, and that gives me 5,040 different ways to type in 4-digit code if I don't repeat numbers. Okay, the second one, we're going to allow you to repeat. So this time I have 10 choices all 4 times because I'm allowed to repeat. I mean, if I want, I could put 3333, right? That's a code. So if I multiply those together, this time, because we were allowed to repeat, I have 10,000 different choices of passwords or security codes. All right, on my last one here, they tell me each digit can be repeated, but the first digit cannot be a 0 or a 1. Well, they just took away 2 choices from me, right? So the first digit, when I go to type in my security code, I can't put a 0 or a 1, but I can put 2 through 9. So this time I have 8 choices for my very first digit, but then for the rest, I have the 10 choices. I have 0 through 9 that I can put in, and I am allowed to repeat. And so that's going to give me, if you multiply those together, 8,000 different ways that I could put a security code in. This is just showing again how those last 3 problems worked. So this is why we started going to passwords having an uppercase letter, a symbol, letters and numbers, because it just makes it harder to figure out your password if someone's trying to hack in. All right, let's try one more, and this is going to show you how big this gets. So let's say you are making a license plate, and there are 6 letters in the license plate. And we're not bringing in numbers. We're only gonna do letters. So there are 26 letters. Each of them can be repeated. So if they can be repeated, then you have 26 choices, right? This is number one. You have 26 choices all 6 times because we're allowed to repeat. I mean, we could do A, right? I don't think I did 6. So 26 to the 6th power is huge. It's almost 309 million different ways you could do that. I know that's hard to believe, but it is true. Now, for number 2, they said, okay, we're still going to use the alphabetical letters, but we're not going to allow you to repeat. So then we have that same issue of we're going to work our way down. The first letter, we have 26 choices. But once we use a letter, let's say we use the letter E. Once we use the letter E, we can't use it ever again. So for the second letter, we only have 25 choices because we can't use the letter we used in the first one. For the next one, we only have 24 choices because, again, we can't use the 2 letters we already used. And we're going to work our way down. If you multiply those together, you get almost 166 million. So you can see it's a big difference. By letting you repeat the letter, there's a lot more choices. If you don't let it repeat, you don't have as many choices. All right, number 3, they have, we're still going to do the 6 letters that we can repeat. However, the first letter cannot be A, B, C, D, or E. So this first letter, we do not have 26 choices. We only have 22 choices because we took out A, B, C, and D. That one gets us to 261 million. And then finally, on this last one, we're going to put a number in the first box and letters that are allowed to repeat in the rest of them. So for my 1 digit, they told me I can only go from 1 to 9, not 0 to 9. So I have 9 choices here for my first digit. And then I have my letters that can be repeated for the last 5. And again, if you multiply those out, you'll see you get almost 107 million.